In May of 2026, a small team of NASA-affiliated researchers quietly published a paper that should have confirmed something simple and expected: that a strange magnetic disturbance Voyager 1 detected years earlier had finally faded away, and that interstellar space around the spacecraft had settled back to normal. That is not what the data showed. 5 years after the event first began, the magnetic field surrounding Voyager 1 still had not returned to what it looked like before. Not close. The region the spacecraft is currently flying through remains, in the researchers' own words, remarkably distinct from the environment that existed there before all of this started. There was no press conference for this one, no dramatic televised announcement. It surfaced quietly, the way most real scientific findings do, buried inside a journal most people will never open, describing a result the paper's own authors clearly weren't expecting to still be reporting 5 years after it began. A disturbance that should have passed through like a ripple on a pond has instead left something behind that looks less like a ripple and more like a permanent scar, one nobody's models predicted, and one that is forcing physicists to rethink some basic assumptions about how the space between the stars actually behaves. Here is what Voyager 1 actually measured, why it matters, and why the mystery is still wide open 5 years after it began. To understand why this finding is significant, you need to understand where Voyager 1 actually is and what it's been doing there for over a decade now. In August of 2012, at a distance of roughly 122 astronomical units from the Sun, Voyager 1 crossed the heliopause, the outer boundary of the bubble. Our Sun's solar wind inflates around the entire solar system and became the first human-made object to enter true interstellar space. Since then, it has continued traveling outward, currently sitting somewhere beyond 160 astronomical units from home, deep inside a region scientists call the Very Local Interstellar Medium, or VLISM for short. It is, right now, functioning scientific instrument our species has ever placed that far outside the protective influence of our own star. And one of the things it's been quietly measuring this entire time is the strength and direction of the magnetic field in the space immediately surrounding it. That measurement matters more than it might sound like at first. For decades before Voyager 1 got there, physicists had to model what the interstellar magnetic field should look like, using nothing but indirect evidence and theory, because no instrument had ever actually been inside that environment to check. Estimates came from studying how starlight gets polarized as it passes through interstellar dust, from cosmic ray behavior, from theoretical calculations built around how our Sun's own magnetic field should, in principle, interact with the surrounding galaxy. All of it was inference, educated guesswork built from a comfortable distance of 93 million miles or more, because nobody had ever had a working magnetometer physically present in the environment being modeled. Once Voyager 1 crossed the heliopause, that changed permanently. Its magnetometer began recording the real physical magnetic field strength directly, continuously, for the first time in the history of science, replacing decades of inference with an actual, ongoing physical measurement. And for the first several years after the crossing, the picture that data painted was relatively calm and steady, largely consistent with what researchers had expected going in, which is exactly why what happened next stood out so sharply against everything that came before it. Then, in the year 2020, something happened that Voyager 1's instruments were perfectly positioned to catch in real time. A distinct pressure front, essentially a compression wave rippling through the interstellar plasma, the same way a shock wave ripples outward from an explosion, sweeps up and pushes together whatever material lies in its path, swept across the spacecraft over a period of about 8 days in May of that year. When it passed, the magnetic field strength jumped abruptly, increasing by roughly 36% almost instantly, and the density of the surrounding plasma jumped by a similar amount at nearly the same moment, the interstellar equivalent of a sudden gust, compressing everything in its path before continuing onward. This kind of event wasn't itself unprecedented. Voyager 1 had already recorded a handful of similar pressure fronts and shock waves rippling through interstellar space in the years since its original crossing, echoes of disturbances launched by our own Sun that had traveled all the way out to interstellar space before finally catching up with the spacecraft. Each one a delayed messenger, carrying news of something that happened back at our star years earlier. What happened next, though, was different from anything researchers had seen before. Instead of settling back down shortly after the initial jump, the way earlier events had, the magnetic field kept climbing. Over the following months, it continued strengthening, eventually reaching a peak of roughly 0.56 nanotesla in mid-2021, more than a year after the pressure front first arrived. To put that number in some kind of perspective, Earth's own magnetic field at the surface measures tens of thousands of times stronger than that. So this isn't a force you'd ever feel or notice directly. But for an environment as sparse and quiet as deep interstellar space, where field strengths are normally measured in fractions of a nanotesla, a sustained climb of this size, held for well over a year, represented an enormous and genuinely unexpected departure from anything researchers had modeled. Researchers studying this pattern gave it a name: the magnetic hump, a prolonged, elevated bulge in field strength that behaved less like a brief shock and considerably more like some kind of slow-moving structure still working its way through the local plasma long after the initial disturbance had technically passed. It took roughly a year and a half from the moment the pressure front first hit for the field strength to decline, back down to somewhere near its immediate post-jump value. That alone was already a strange enough result to justify its own published study back in 2023, when Leonard Berlanga and his colleagues first described the hump and proposed that it likely represented a compression wave still propagating through the very local interstellar medium long after the initial front had swept past. But here's where this story picks back up in 2026, and where it starts to genuinely unsettle the researchers involved. A team led by Jiwoo Park at NASA's Goddard Space Flight Center working alongside longtime Voyager researchers, including Leonard Berlanga, one of the scientists who first identified the magnetic hump back in 2023, went back through the data with a much longer timeline in front of them, tracking Voyager 1's magnetic field measurements all the way from the original 2020 pressure front through mid-2025, more than 5 full years of continuous observation. If the magnetic hump had simply been a temporary disturbance working its way through the interstellar plasma, the expectation, based on how these kinds of compression waves are supposed to behave, was that the local magnetic environment should have eventually returned to roughly the same baseline conditions that existed before the pressure front ever arrived. That's what compression waves generally do. They pass through, they leave a temporary spike behind, and then things settle back down to whatever they looked like before. That is not what the 5-year dataset showed. According to the published results, the magnetic field environment in what researchers call the post-hump region, the stretch of space Voyager 1 has been traveling through ever since the hump technically ended, remains remarkably distinct from the region the spacecraft passed through before that second major pressure front ever arrived back in 2020. In plain terms, years after the disturbance supposedly ended, the neighborhood Voyager 1 is currently flying through still doesn't match the neighborhood it left behind. Something about that 2020 event appears to have permanently altered the character of the local interstellar magnetic environment, not just temporarily disturbed it and let it settle back to its original state, the way a ripple settles back into still water. There's a second, quieter layer to this mystery buried inside the same body of research, and it involves not just how strong the magnetic field is, but how chaotic or structured its fluctuations actually are. A property researchers call intermittency. Think of it as the difference between a perfectly smooth, predictable hum and a jagged, unpredictable crackle. During the years leading up to the magnetic hump, and continuing through the hump itself, the small-scale fluctuations in Voyager 1's magnetic field data followed a specific kind of statistical pattern called a Solace distribution, sometimes referred to as a Q-Gaussian, a mathematical signature typically associated with complex, turbulent, far from equilibrium systems, the kind of chaotic structure you'd expect from a plasma still actively churning and reorganizing itself, jostling and rearranging in ways that don't settle into a simple, predictable pattern. But once the hump ended, sometime around 2022, that pattern appeared to shift. The fluctuations in the data started looking much closer to an ordinary, well-behaved Gaussian distribution, the kind of statistical pattern associated with calm, settled, near-equilibrium systems. Essentially, statistical noise behaving. The way basic textbook physics says noise should behave once a system has had time to settle down. On the surface, that looked like confirmation that things really had calmed back down after the hump. A tidy resolution to an otherwise strange story, except more recent, more careful reanalysis of that same data has complicated that tidy conclusion considerably. A separate 2025 study led by researcher L.Y. Koo, using a more sophisticated statistical method built around fitting what are called kappa distributions rather than simple Gaussian curves, a technique better suited to teasing out subtle structure hiding underneath apparently random noise, found that the apparently calm, Gaussian-looking behavior researchers initially reported may actually be at least partly an artifact of having a limited amount of data to work with, rather than genuine proof that the underlying turbulence had settled down. According to that reanalysis, meaningful residual intermittency, meaning real underlying chaotic structure, appears to persist in the data even during the stretch that initially looked calm on the surface. In other words, the interstellar medium around Voyager 1 might not have actually settled back into a simple, orderly state at all. It might simply be behaving in a way that's harder to detect with a smaller sample of data, hiding real complexity behind what looks, at first glance, like ordinary statistical noise, a distinction that matters enormously to physicists, even though it would be functionally invisible to anyone without a background in the specific mathematics involved. Put those two findings together, the persistently altered magnetic environment and the ongoing uncertainty over whether the underlying turbulence has genuinely calmed down or is simply harder to measure, you get a picture considerably messier and more interesting than anyone expected. back when Voyager 1 first crossed the heliopause in 2012. For years, the working assumption among many researchers was that the interstellar medium, once you got past the immediate chaos right at the heliopause boundary itself, would behave as a relatively calm, largely uniform background environment, occasionally disturbed by solar-driven shocks and pressure fronts that would pass through and then fade, leaving the underlying medium essentially unchanged in the long run. The same basic assumption that lets scientists model interstellar space as a simple, well-behaved backdrop against which more interesting things happened elsewhere. What Voyager 1's data now suggests, 5 years and counting after a single pressure front rippled through in 2020, is that this assumption may be fundamentally wrong. The interstellar medium may have something closer to memory, a capacity to be genuinely, structurally altered by a single passing disturbance in ways that persist for years afterward, rather than simply reverting once the immediate shock has passed. The cosmic equivalent of a landscape that doesn't simply spring back into shape after a storm passes through, but is instead left permanently reshaped by it, its contours subtly different from that point forward. Researchers studying this event have proposed that the 2020 pressure front likely originated at the Sun itself, launched during the declining phase of an earlier solar activity cycle, then traveled outward for years, before finally slamming into the interstellar plasma tens of billions of miles away. That connection matters because it means events happening at our own star, routine, largely unremarkable solar activity from our perspective here on Earth, can apparently leave a mark on the actual physical structure of interstellar space itself, one that persists for years after the event that caused it has technically ended. It's a genuinely strange thing to sit with. A disturbance from our own sun, launched years before it ever reached Voyager 1, may have permanently reshaped a stretch of the galaxy immediately surrounding our solar system, in ways scientists are still working to fully characterize. This connects directly back to something else researchers had already discovered at the heliopause boundary itself, the finding that the sun's magnetic field and the galaxy's surrounding magnetic field aren't cleanly separated the way earlier models assumed, but are instead linked through a process called magnetic reconnection, where field lines from different sources interact and exchange energy directly. Snapping and reconnecting in new configurations, the same way tangled power lines might momentarily fuse together and release a burst of energy before settling into a new arrangement. If the solar and interstellar magnetic environments really are connected in that way, rather than existing as two isolated systems meeting cleanly at a fixed boundary, then it becomes considerably less surprising, though no less remarkable, that a disturbance originating deep inside our own solar system could ripple outward and genuinely restructure the interstellar environment for years after the fact. The heliopause, in other words, may not function as a clean, one-way barrier, the way textbook diagrams have long depicted it, a simple wall separating everything that belongs to us from everything that doesn't. It may behave more like a permeable membrane, one capable of transmitting real, lasting structural change from one side to the other, carrying the consequences of our own star's behavior out into a region of the galaxy most people assume has nothing whatsoever to do with us. All of this arrives at a genuinely relevant moment. Solar cycle 25 reached its predicted peak activity around the middle of 2025, meaning our sun has spent the past year or so producing a noticeably higher rate of the kind of eruptions capable of generating exactly this type of pressure front, sending fresh waves of compressed plasma outward on the same multi-year journey the 2020 event once made. Some of the same researchers modeling these events have projected that Voyager 1's twin, Voyager 2, still trailing behind at a somewhat shorter distance from the sun, may encounter a comparable shock or pressure front of its own sometime around 2024 to 2025, give or take roughly half a year. A prediction that puts a fresh, independently measurable test of this entire phenomenon directly in the window we're currently living through. Because Voyager 2 still carries a working direct plasma instrument, unlike Voyager 1, whose equivalent instrument failed decades ago, any future disturbance it encounters could actually be measured two different ways at once, offering a level of confirmation Voyager 1's own 2020 event never had the luxury of. If Voyager 2 experiences a similar prolonged magnetic disturbance following its own encounter, one that likewise refuses to fully settle back to baseline for years afterward, that would move this finding from a single strange anomaly recorded by one aging spacecraft into a genuine, repeatable pattern in how the interstellar medium actually responds to solar-driven disturbances, a pattern current models simply were not built to predict. That word, repeatable, is really the heart of why researchers are taking this so seriously instead of writing it off as an odd quirk in one instrument's readings from one aging spacecraft. Science generally treats a single strange result with healthy caution because instruments degrade, data can be misread, and unusual patterns sometimes resolve into mundane explanations once more data comes in. But here, the researchers went back specifically to check whether this anomaly would resolve into something ordinary given enough additional years of observation, and instead of fading into an unremarkable footnote, it deepened. 5 years after the initial event, the disturbed region still looks meaningfully different from what came before it, and the character of its underlying turbulence remains genuinely disputed rather than settled. That is precisely the kind of result that ends up forcing revisions to established models, not because any fundamental law of physics has been broken, but because the actual behavior of a real physical system, measured directly for the first time in history, is turning out to be considerably more complex, more persistent, and more interconnected with events happening back at our own star than anyone modeling it from a comfortable distance ever predicted. And that ultimately is what makes Voyager 1 continue to matter this deep into its mission, nearly 49 years after launch, running on a fraction of its original power, slowly losing instruments one by one as its plutonium generators keep decaying year after year. It is still the only object in existence capable of directly measuring these events as they happen, rather than modeling them secondhand from 93 million miles away, sitting comfortably behind a telescope on a planet the disturbance in question never actually touches. Every additional year of data it manages to send home is another chance to determine whether this magnetic hump was a one-time fluke or the first confirmed example of something genuinely new about how our solar system and the galaxy immediately surrounding it interact. And every year that question stays open is another year. Scientists spend building models on an incomplete picture of the only interstellar environment we've ever actually been able to touch. There's no backup instrument waiting to pick up where this one eventually leaves off. No second Voyager 1 sitting in a warehouse ready to launch and catch up to nearly 50 years of head start. Whatever gets measured between now and whenever this spacecraft finally falls silent is, for the foreseeable future, all the direct evidence humanity is ever going to have about how a disturbance from our own star can reach out and permanently reshape a piece of the galaxy around us. If stories like this are what you come here for, hit subscribe, turn on notifications, and let me know in the comments whether you think Voyager 2 is going to show the exact same pattern when its own pressure front finally arrives. Because if it does, this stops being one spacecraft's strange anomaly and starts being a real confirmed rule about how our sun quietly reaches out and reshapes the space between the stars.